Here's a puzzle that feels impossible. A bucket is dropped from a ladder. At the very same instant, someone throws a ball to hit it in midair. Where should they aim? The surprising answer. Aim straight at the bucket's starting spot, and you hit it no matter how hard you throw. Let's state the problem precisely. A person stands on a ladder holding a pail. At a height h1 above the ground, that person releases the pail from rest. At the very same instant, a second person standing a horizontal distance as away throws a ball to hit the pail. The thrower releases the ball at a height h2 above the ground with initial speed v0 at an angle θ0 above the horizontal. We assume v0 is large enough that the ball reaches the pail before hitting the ground, and we ignore air resistance. We want three things: the aiming angle, the time of collision, and the height where the two meet. First, set up coordinates. Put the origin on the ground, directly beneath the point where the ball is released. The positive y direction points up, and the positive x direction points toward the pail. There are two objects, and each is in free fall, so each has just one stage of motion. The pail moves in one dimension straight down. Its horizontal coordinate stays fixed at x1 equals s, and its height is y1 of t. The ball moves in two dimensions, starting at the origin's horizontal position with height h2. Its coordinates are x2 of t and y2 of t. Now write the equations of motion for both objects. The pail starts from rest, so it has no initial vertical velocity. Its height is v1 of t equals h1 minus 1 half gt squared, and its vertical velocity is minus gt. The ball is more involved. Its horizontal position is x2 of t equals v0 cosine theta, naught times t. And since nothing accelerates it horizontally, its horizontal velocity stays constant at v0 cosine theta naught. Vertically, the ball starts at height h2 with upward velocity v0 sine theta naught, so its height is y2 of t equals h2 plus v0 sine theta naught times t minus 1 half gt squared, and its vertical velocity is v0 sine theta naught minus gt. These are the full equations for both objects. What pins down the answers is the collision itself. At the collision time, call it TA, the two objects are at the same place. Same place means two things. First, their heights match. y1 at TA equals y2 at TA. Second, the ball has traveled the full horizontal distance to the pail. x2 at TA equals s. These are the two extra conditions we need. Writing the height condition out gives h1 minus 1 half gta squared equals h2 plus v0 sine theta, naught times t minus 1 half gta squared. The horizontal condition is s equals v0 cosine theta naught times ta. Watch what happens in the height equation. Both sides carry the same minus 1 half gta squared term, so they cancel completely. That cancellation is the heart of the trick. Gravity pulls the ball and the pail down by exactly the same amount in the same time, so it drops out. What's left is clean v0 sine theta naught times ta equals h1 minus h2. Now divide this by the horizontal condition, s equals v0 cosine theta naught times ta. On the left, v0 and ta divide out, leaving sine over cosine, which is the tangent. So tangent of theta naught equals h1 minus h2 over s. The speed and the time have vanished entirely. So the aiming angle is theta naught equals the inverse tangent of h1 minus h2 over s. Notice what's missing. There is no v0. The angle does not depend on how hard you throw. And the answer has a beautiful meaning. Look at the right triangle it describes. The horizontal leg is s, the vertical leg is h1 minus h2, the difference between the pail's starting height and the ball's release height. An angle whose tangent is rise over round points straight along the hypotenuse. That line aims directly at the pail's initial position, so you simply aim at where the bucket starts and trust gravity to take care of the rest. Now for the collision time. We have two equations, V0 sine theta, naught times Ta equals h1 minus h2, and V0 cosine theta naught times Ta equals s. There's a clean way to combine them. Square both equations. The first becomes V0 squared sine squared theta naught times T squared equals h1 minus h2 all squared. The second becomes V0 squared cosine squared theta naught times Ta squared equals s squared. Now add them. On the left, factor out V0 squared Ta squared, and the sine squared plus cosine squared is exactly 1. So the left side is just V0 squared Ta squared. The right side is s squared plus h1 minus h2 squared. Take the square root, V0 times Ta equals the square root of s squared plus h1 minus h2 squared. Solving for the collision time, divide by V0, Ta equals 1 over V0 times the square root of s squared plus h1 minus h2 squared. This makes physical sense. The square root is just the straight line distance from the ball's release point to the pail's starting point by the Pythagorean theorem. So the collision time is that distance divided by the launch speed. Throw harder and the V0 goes up, so Ta goes down, and the two meet sooner. Now we can also find the height of the collision. The pail's equation is the simplest, since it started from rest, so we plug Ta into y1 of t. Substitute the collision time into the pail's height. Recall y1 of t equals h1 minus 1/2 gt squared. Plugging in Ta, we square it, and the square of 1 over V0 times that square root is simply s squared plus h1 minus h2 squared all over V0 squared. So the collision height is y1 at Ta equals h1 minus g times s squared plus h1 minus h2 squared divided by 2 V0 squared. That's the answer to part C. It sits a little below where the pail started by exactly how far the pail has fallen by the moment of impact. There's an even slicker way to see all of this. Imagine watching the whole thing from a reference frame that itself accelerates downward at g. In that frame, gravity is cancelled out. Neither object accelerates at all. The pail just hangs there, perfectly still at its starting point, and the ball travels in a straight line at its launch speed V0 along the launch angle theta naught. To hit a stationary target, you obviously aim straight at it, which immediately gives the angle, the inverse tangent of h1 minus h2 over s, and the time to reach it is just the straight line distance over the speed, which is exactly Ta equals 1 over V0 times the square root of s squared plus h1 minus h2 squared. Same answers, no equations to cancel. Aim where the target starts and let gravity pull you both down together. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.